In Chapter 8, we're going to learn about acids and bases.
The first thing is, how do we recognize what is an acid or a base? The simplest definition is that an acid is a compound that has hydrogen first in its formula. Any compound that has hydrogen first in its formula will do what this acid, hydrochloric acid, is doing in water. That is, it will break apart or dissociate into a hydrogen ion and the counter ion here, which is chloride. Bases can be defined in a similar way, and you can say a base contains hydroxide, so that when it dissolves in water and dissociates, it will form a hydroxide ion plus the counter ion, which here is the sodium ion. These are called the Arrhenius definition of acids and bases. It's the simplest one, and really, for the most part, you're going to probably understand acids and bases best by this definition. The definition is limited, though, and sometimes it is inaccurate. For instance, hydrogen ion doesn't exist in water. Instead, it reacts with the water to form the hydronium ion. If you look in this picture, you can see that the hydrogen ion, or what we call a proton, will attach to a water molecule and make this new ion with 3 hydrogens attached to an oxygen and a positive charge on the oxygen. This is what's really present in water rather than a proton. No naked proton exists in water. A broader definition of acids and bases is the Bronsted-Lowry definition. A Bronsted-Lowry acid and base are just considered proton donors and acceptors. So all we do is we look to see what's giving up a proton, that's our acid, and what's taking a proton, that's our base. So if we look at this reaction here, we see hydrochloric acid has a proton on it. The chloride in there is giving up that proton. You can see it on the other side of the reaction as chloride aqueous. Because hydrochloric acid is giving up that proton, we call it an acid, according to the Bronsted-Lowry definition. If I look at water, it actually picks up that proton from the hydrochloric acid. After the reaction is complete, if you look on the product side, you will see the hydronium ion, which is basically water with a proton added to it. So water is considered a base in this reaction because it accepts a proton. Bronsted-Lowry acids must contain a hydrogen atom, and it's usually written first in the formula. And you can see hydrochloric acid, hydrobromic acid, nitric acid, sulfuric acid. And then down there you see acetic acid, and that doesn't really fit the format we've been seeing. So far we've been seeing a hydrogen written first in the formula. We can rewrite acetic acid so that hydrogen that's in red is written first in the formula, and we sometimes write it as hydrogen, or H, and then C, H3, CO2, to emphasize that the hydrogen is, the hydrogen written formula is a proton, but that's not structural because hydrogen is really attached to the oxygen. Regardless, you're expected to recognize an acid when the hydrogen is written first in the formula. Now, acetic acid is one of what we call carboxylic acids. That is a type of acid that we find in organic chemistry. Later on in this course, we will look at organic chemicals, and we will have to recognize organic acids, but that's later on in the course. A base can only accept a proton because it has a lone pair of electrons. That lone pair of electrons can form a bond to a proton, and that is what makes it a base. So if you look at this reaction here, ammonia has a lone pair of electrons. that lone pair of electrons can reach out and grab a proton from water, you see in the reaction water's written right there, and pull that proton off. When it pulls the proton off, the proton is then attached to the lone pair. In other words, it makes a bond with the nitrogen at the lone pair site. This makes the ammonium ion that we have written on the right side of the reaction. And left over from that, because when you remove a proton, H+, from water, you remove one of the hydrogens, and if you remove a positive, you must leave a negative behind. And so what's left over is that hydroxide on the right side of the equation. This is how Bronsted-Lowry bases work. Here is a list of many bases. On the left, you have compounds that have lone pairs on them that can pick up a proton. Ammonia can pick up a proton on its lone pair. Water can pick up a proton on its lone pair. These are all bases because they can pick up protons. On the right side, you have metal hydroxides. Hydroxides have lone pairs on them where a proton can attach. A hydroxide can react with a proton and make water, and that is what hydroxide compounds will do. The compounds on the right are very easy to recognize as a base because metal hydroxides are all bases. Now, the compounds that have lone pairs on them are a lot harder to identify, and I'm not going to expect you to be able to recognize all of the possible bases when they have lone pairs. I only expect you to be able to show how they behave as bases when I tell you that they are one. Let's look at see what happens when an acid and a base react together. You can see down here, HA is a common way of writing an example acid. So it has a proton attached to the rest of the molecule A. That acid can react with a base that has a lone pair on it. That could be hydroxide or it could be ammonia. It's anything that will accept a proton. What happens is the lone pairs on the base reach out and grab the proton from the acids. That means that the base gains that proton, leaving the rest of the acid without the hydrogen and with a negative charge left behind. When you take a positive away from a molecule, you must leave a negative behind. At the same time, after the base has picked up the proton, because it's taking away a proton which has a positive charge, it must have a positive charge after the hydrogen is attached to it. How is it that this negative charge results on the rest of the molecule of the acid? It's because when that hydrogen breaks the bond between the hydrogen and the acid, the electrons that are in that bond jump back onto the rest of the acid molecule. That's what gives it the negative charge. Likewise, how is it that the base now has a positive charge? When that hydrogen went over to the base, those lone pairs reached out and formed a bond with the hydrogen. You had two electrons that formerly were only on that base, and now half the time those electrons are on hydrogen. That leaves a positive charge on the base. I think it's a lot easier to understand this reaction, though, if you look at it that H plus is leaving HA. Hydrogen leaves and a plus leaves. If a plus leaves, it must leave a negative behind. When hydrogen jumps onto the base, it's bringing over with it that positive charge. So what results? Hydrogen attached to a base with a positive charge. Let's look at this reaction again by labeling it. On the left side you have HA, which is our acid, and B, which is our base. Afterward, that acid has lost its proton, so it is no longer a proton. However, it could pick up a proton and go back to HA, couldn't it? Because it could do that, it's a base. We call it the conjugate base of the acid. The base is a base because it picks up a proton. On the product side of the reaction, you see the base with the proton attached. However, the base could give up its proton. If the base gives up a proton, well, then it's an acid. So we call B the base, and when the proton's attached to it, we call it the conjugate acid. These are actually called conjugate acid-base pairs. One conjugate acid-base pair is the acid plus its conjugate base. The other conjugate acid-base pair is water plus the hydronium ion. Right here we're actually seeing a real acid react with a real base. Hydrobromic acid is a real acid. It gives up its proton to the base water. Afterwards, you have left over bromide, which was a hydrobromic acid, but now it had its proton removed. And we have the hydronium ion, which used to be water, but now that the proton attached to it, it's the hydronium ion. And so you can see how these are conjugate acid-base pairs. Notice the sum of charges on the reactant side is all zero. And if you sum up the charges on the right-hand side, 1 negative plus 1 positive, that's also equal to 0. This is a little rule that we have in chemistry, is that charge is conserved. On the reactant side, if you have a particular charge, it must be that same charge on the product side. So now what I'd like you to do is to stop and try to do this yourself. Figure out what is the conjugate base of carbonic acid. Remember, to figure this out, what you need to do is write the equation that shows how it behaves as an acid. So you're going to write the dissociation equation. To figure out what is the conjugate acid of ammonia, I've written the reaction that shows how it behaves as a base. And then down there at the bottom, what is the conjugate acid of hydroxide? In order to figure out what is the conjugate acid of hydroxide, show how it behaves as a base. So to figure out what is the conjugate base of carbonic acid, the first thing you would have to do is write a dissociation equation. Now, I've given you 3 possibilities. There's really 4. But the first one is the most simple one, which is showing carbonic acid losing just 1 proton, and it makes bicarbonate and a proton. Of course, some people don't like writing a proton all by itself, so you could write that same reaction in the next line using water to pick up the proton and then forming the hydronium ion. It's a little more complicated looking, but it says exactly the same thing as the reaction before. Some people like to take both protons off, and that's valid too. This is called a diprotic acid, and it does lose 2 protons, not all the time. It will lose 1 and it will lose 2 at any point in time. It's a little bit more complicated than what we're going into, but any one of these reactions is valid, and there's even a 4th one I haven't written, which is to take carbonic acid and 2 waters and to make carbonate and 2 hydronium ions, and that's completely valid too. Now, once we've written these dissociation reactions, that's when we can figure out what is a conjugate base. Let's look at the first reaction on top. Carbonic acid forming bicarbonate and a proton. Basically, you can say to yourself, when something is behaving as an acid, it produces a proton plus the conjugate base. So whatever is not the proton is the conjugate base. So the bicarbonate is the conjugate base of carbonic acid. If I look at the next one, I can look at it the same way. Carbonic acid plus water forms bicarbonate in the hydronium ion. And you can say to yourself, it's an acid because it forms a hydronium ion. The rest of what is formed is the conjugate base. So the conjugate base is bicarbonate. If I'm looking at it forming two protons, as in the last reaction, then you can say carbonic acid forms two protons plus carbonate. The two protons are produced because it's an acid, so the carbonate is a conjugate base of carbonic acid. Notice there are two possibilities of a conjugate base of carbonic acid, and both of them are considered conjugate bases of carbonic acid. So let's do this problem now. What is the conjugate acid of ammonia? Again, like the acid, we have a reaction that shows how it's behaving as a base. It's a base because it's producing hydroxide, isn't it? The ammonium, NH4+, is what is left over besides the hydroxide. See, bases produce hydroxide in water, the Arrhenius definition. It's the simplest one. So you say it's a base because it's producing hydroxide, so the conjugate acid is ammonium. To determine the conjugate acid of hydroxide, we write how it behaves as a base. Hydroxide is a base because it will pick up a proton. When it picks up a proton, it makes water. Therefore, the only thing that can be the conjugate acid of hydroxide is water.